right, so today we're going to talk about rigid versus non-rigid transformations. Now, we've already talked about 3 rigid ones. The word rigid simply means congruent. So a rigid transformation will also be known as an isometry, and that's where your preimage and your image do remain congruent. So we've talked about translations, reflections, and rotations. And you'll see I've attached this little transformation cheat sheet because we did talk about how we could write the rule if we're reflecting over the x or y axis or along our diagonals y equals x and y equals negative x. We had to use the rules when we did rotations, which were always counterclockwise. And then we also had our translation rules. You will be given this little cheat sheet on your quiz. So I don't expect you to memorize all of this. I would love for you to, but I'm not going to ask you to. All right, now, if they're not rigid, then they will be non-rigid. So simply, a non-rigid transformation is one where your pre-image and image do not remain congruent. Now, there's a special one that's called a dilation, and we'll talk more about this when we get to the unit on similarity. But for now, you just need to know that this is when your pre-image and image, they stay the same shape, but they'll be different sizes. So they're either going to get larger or smaller. In order for that to happen, both the x and y coordinates have to be multiplied by the same value. So you will see a rule that looks like this. Given any ordered pair, you can multiply the x and y coordinate by the same value. Might be 1/2, might be 2, might be 8, could be anything. So what this would be called, you would tell me that this is a dilation and that it has a scale factor of whatever number is being multiplied to it. So this has a scale factor of 1/2. If both the x and y coordinates are not multiplied by the same number, then we're just going to say it's a non-rigid transformation. We can't give it a special name because these won't be the same shape or the same size. All right, so you'll have the ordered pair and you'll see something like this. So in this case, just the y coordinate is being multiplied by a different number. So we would say this is a non-rigid transformation with a, now think about the y coordinate. The y coordinate moves things up and down, right? So that is going to be a vertical stretch and then a factor 2, whatever number is being multiplied by it. In the second example, it's the x coordinate that's being multiplied. So again, just the x means it's non-rigid, but the x will move this horizontal. So this is a horizontal stretch of a factor 1/4. Now, technically, when our numbers are smaller than 1, they're not really stretches. You can call that a compression or a shrink. But for right now, what's important is I want you to recognize what the direction is, okay? And we're just going to call it a stretch to keep everything simple for now. All right, so let's look at some examples I expect you to do with this. All right, this first example, first it wants us to name the type of transformation, and then we're going to prove whether the transformation is actually rigid or non-rigid using our distance formula. Now, there's 2 ways that you can identify the rule. You can look at our ordered pairs that are given, since they are, and find the pattern, all right? And it's always difficult with 0 being a coordinate, because when I look at just the j and j prime, I can tell that the y was made opposite, and then they were switched. But if we look at k and k prime and l prime, we'll see not only was the y made the opposite and switched, so was the x. So if we look at our rule, any ordered pair, what was happening was the y was made negative and moved front, the x was made, I should say the opposite, not negative, and moved to the back. And if you look at your little cheat sheet, all right, and find that pattern, you'll notice that what this was a reflection, right, across y equals negative x. All right, now what we're reflecting is a triangle. So behind it, we would put triangle JKL or whatever order you want to name. So that would be the type of transformation. You can also look at the picture, since there's one given for this problem, And hopefully, if you can tell that J moves to J prime and L to L prime and K to K prime, that it is reflecting over this diagonal with the negative slope. We can draw it in, okay? And now you can see that that is y equals negative x. The other way that I will allow you to describe it or to name it, all right, is that you can tell me it's a reflection using words through, but be specific, y equals negative x. All right, just don't tell me it's a reflection and stop there. Be very specific. So that's the naming part. Now the proving part, we're going to use the distance formula. So what we need to prove is that JK and J prime K prime are the same. Now, thankfully, we have a picture. So notice those are both horizontal and vertical. So I'm just going to count those, right? So I know JK is 1, 2, 3, 4. And then I know J prime K prime, if I count the vertical, is also 4. So that one's done. I really didn't need to use the distance formula for that. So pay attention to the horizontal and verticals. That makes it simple. But we do have to do then side JL and side KL. So let's start with JL. All right, so I'm going to use the points J and L from up above. So I'm going to subtract the x's, 0 minus 2, square that, plus, and then I'll subtract the y's, which will be 3 minus 1. Remember, go in the same order that you subtracted the x coordinates. So we would get the square root of negative 2 squared plus positive 2 squared. So both of those turn into 4 and 4, so we get the square root of 8. Now I'm just going to leave it like that for now, because if this is rigid, which it should be, then when I do J prime L prime, and I can show that that also equals the square root of 8, we can just stop there. We don't need the decimal. All right, J prime L prime. So we've got negative 3 minus a negative 1, square that, and then we'll have 2 minus negative 2, or I'm sorry, 0 minus a negative 2. Do what I write, not what I'm saying. All right, 0 minus negative 2. So those double negatives are really positive. So I've really got negative 3 plus 1. So that'll get me negative 2 in the first group. And then again, we'll have, that will turn into a positive 2. So once again, I see I've got 4 plus 4, which is the square root of 8. So we've proven 2 sides so far. Now we need to do the third. All right, so we now need to do KL. All right, points K and L, so I'm going to do 4 minus 2, quantity squared, plus, and then I've got 3 minus 1, quantity squared. So we'll have 2 squared plus 2 squared is going to be 4 plus 4, which again is the square root of 8. And then KL, or K prime L prime, sorry, let's write the correct thing, is going to be the square root. And then we've got negative 3 minus a negative 1 squared plus negative 4 minus a negative 2 squared. Again, those double negatives are really positive, so negative 3 plus 1 is negative 2 that we're squaring in the front. And back here, negative 4 plus 2 is another negative 2 squared. But they both turn positive 4. All right. So we have proven that all 3 sides remained congruent. These figures are congruent. So we've proven that this would be rigid. Okay, let's just write that, rigid. All right, let's look at the second example. Second example, we didn't get a coordinate plane. All right, but it wants us to name the type of transformation. So let's look at the ordered pairs. All right, so over here, we've got these ordered pairs x, y. So let's look at what's happening to them. Well, the x coordinates are definitely not the same, but the y coordinates are. So I know that the y's didn't change. I can put that down. So you kind of have to figure out what's happening to my x coordinates. And what appears to me, and hopefully to you too, is that they're all being doubled. So we're multiplying everything by just the x coordinate by 2. So when it says name the type of transformation, since only one of the coordinates is being multiplied by something, this is going to be a non-rigid transformation. But now you can explain to me what kind of stretch. Is it horizontal or is it vertical? And since it's the x that's being multiplied, this is a horizontal stretch of factor 2. Okay, now we're going to prove it. So we've got 3 sides. So we're going to need to prove that FG is different from F prime G prime. All right. And actually, in order to prove that it is non-rigid, we just need to show that it's not congruent. So if you can show me that one side pair of the pre-image and the image are not congruent, then we'll be able to stop there to show that it is actually non-rigid. So let's see what we get. So F and G. So subtract the x's. So we've got -1 minus 1 quantity squared plus, and then we'll have 1 minus -1 the quantity squared. So that gives me -2 that I need to square, and then a +2 that we need to square. Again, like above, and this does not always happen, we get the square root of 8. That seems to be a popular answer today. All right, let's do the primes. So we'll subtract the 2 x coordinates. So I've got -2 minus 2, and I'll square that, and then 1 minus a -1. So in the front, we have a -4 we're going to square, and then a +2 to square. So now we've got 16 plus 4, so we'll have the square root of 20. But again, these are not equal. So this is non-rigid. All right, so now again, assuming that we didn't make any math mistake, we can conclude what type of transformation that we said it was, it actually is. All right. The last part of this lesson is on symmetry. And there are 3 kinds of symmetry that you need to be able to identify. One is line symmetry, also known as reflection symmetry. All right. I don't care if you use the word line or reflection, just make sure the word symmetry comes after it. All right, and so this is when a line can be drawn through a figure that's going to create 2 halves, each one being a mirror image of the other. So there may be just one line of symmetry, there could be more than one, or there might not be any line symmetry at all. So the letter F, this doesn't have any lines of symmetry. I can't draw one, and of course we always start with the horizontal and verticals, and then we look at maybe diagonals, right? And there aren't any, so we would just say no lines of symmetry. Right, the letter E does. All right, I can actually draw a horizontal line right through that middle right there, and I create 2 equal halves that are mirror images of each other. That's the only line I can draw, so it just has one line of symmetry. Now this square, I've got it sitting sideways, but I can draw a horizontal and create those 2 mirror images. I can draw a vertical. But with the square, because these are right angles only, I can also do some diagonals because I'd get 2 little rectangles on each that would be mirror images of each other. All right, so there are many lines of symmetry there that we can draw. All right, point symmetry. Point symmetry is when a figure can be mapped onto itself by rotating the figure exactly 180 degrees about a center point. So when I look at this letter S, all right, if I think about there being a point right in the middle and I rotate it basically upside down, that would be 180 degrees, that letter S would look the same. All right, in a deck of cards, we've got, in fact, every card in the deck, there's a point in the middle that we can rotate it and turn the cards upside down and they will look exactly the same. All right. But then it can also have just rotational symmetry. And this is when a figure can be mapped onto itself by rotating a number of degrees less than 180 degrees, again, about a center point. So some figures will not have rotational symmetry at all. Excuse me, let's get that up. And if they do, we're going to be able to identify what's called the angle of rotation. I'll slide this over a little bit. All right, so down here, the letter A does not have rotational symmetry. All right, there's no way to rotate that figure around any number of degrees where it's going to look exactly the same as it does in its original position. All right, but letter B does. This is a hexagon. All right. Now again, here's your center of rotation, just kind of like when we just talked about point symmetry. All right, so we can rotate this picture around, and at certain places, it's going to look exactly the same. All right, now I can rotate the paper without hopefully not making you too dizzy, right? But if I turn it, look, there's my hexagon, same way it looked before. I can turn it a little bit more. There's my hexagon, the way that it looked before. All right, so we just need to find that one place. So what you're going to do is you're going to draw a ray up through one easily identifiable corner in your picture. And then if we turned, where would we meet that identical corner again? And we would draw a second ray. The angle that those rays create, this is your angle of rotation right here. Okay. So how do we figure that out? Well, how many times can I create that angle? So that's 1. This would be 2. And then we've got 3, 4, 5, 6. So you take a full rotation, which is always 360 degrees, and divide it by the number of angles you can create. And that gets you your 60-degree angle of rotation. Okay. All right, so just to clarify, if something has point symmetry that we talked about above, then it will have 180-degree rotational symmetry as well. So it can have point symmetry if it's exactly 180, but there's nothing wrong with saying that it also has rotational symmetry of 180 degrees. All right, so those are the 3. And so real quick, let's just look at some some problems. So it asks, how many lines of symmetry does each figure have? Now, if you remember in the example, my square had right angles, all right? Parallelograms and rhombuses, all right, which do not have 90-degree angles, are not going to have any lines of symmetry. You can't draw one horizontal, okay? In fact, I'll try to do it for you. I don't want you to do it. But you can see that my left side's longer than my right. And the same thing happens down here. So that can't happen. So there are no lines of symmetry. Right? Look for those right angles. So in this picture, we've got lots of right angles. I can draw, right, vertical, horizontal, and I can even the diagonals will work. All right, so I've got 4 lines of symmetry here. And then our heart, the only line I can draw that creates 2 equal halves is a vertical line. So this has 1 line of symmetry. All right, so in order to have line symmetry or reflection symmetry, you only need to find 1 line. That's it. All right, just one line and then it will have it. All right, this middle row, it says, do any of the figures below have rotational symmetry? And if so, give the degrees. All right, well, remember, here's your center of rotation, should be in the middle. And I can draw a ray up through this arrow. And then if I turn my paper, if you want to, I'm going to hit that same spot right here. So by looking at that, I hope you can tell that is a 90-degree angle, because we would be able to get, right, 1, 2, 3, 4 of those. So we would take 360 divided by 4. So this has 90-degree rotational symmetry. All right, our star, it does, all right, as I rotate it, it's going to look the same. I can go up through here, and then its matching corresponding point would be here. All right, so that's 1, and then we've got 2, 3, 4, 5. So 360 divided by 5, it's going to give me, I believe, 72 degree rotational symmetry. All right, our pentagon, actually, it's going to be the same, right? So this also has 72 degree rotational symmetry. Now this hexagon, this one looks a little squashed. So if I turn my paper, yeah, it's definitely, that's longer that way. So the only way that this looks the same is if I turn it completely upside down, right? So if I go out this way and then I go out that way. So this is going to have 180 degree rotational symmetry. All right, this baby's got lots of points. So we would go here, and then the next one would be here. So how many of those can we draw? I'm not going to draw them all in, but let's count. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, 360 divided by 16, 22.5 degree rotational symmetry. Okay. Now the bottom just said, okay, did any of those also have point symmetry? And the only one that looked, well, there's 2, I guess, that look identical upside down with 180. All right. And that would be this first one. It would have been our hexagon and this one. All right. You'll also know, because if you take 180 and divide it by that measure, it needs to go in even, right? So 180 can be divided by 90. 180 obviously can by 180, and 180 can by 22.5. If you do 180 by 72, that does not come out even. Okay. All right, you should be ready to do the symmetry and also your rigid versus non-rigid worksheets.